So at the end of last class, Cass asked me about control groups, and we were talking about control groups for the anti-bullying thing. And Cass indicated the idea with a control is that a good control would mean that nothing has happened. So you would want to control an anti-bullying intervention with nothing. So look at some schools that are doing nothing with some schools that have the anti-bullying intervention. Does that make sense? Now, that would make a lot of sense in the way that a lot of people talk about control. But why would that not necessarily be a great form of control? This has to do with balance.
Because they're still not being exposed to the same general situations. So you give them the exact same up to a certain point and then only give the experiment part to the experimental group, but then they are excluded from the experiment themselves.
That's right. So the one control group that we talked about was having the real anti-bullying intervention that we're interested in with some pseudo anti-bullying intervention. And Cass and I discussed what the difference might be. And you can imagine that there are lots of anti-bullying interventions that have been done at various institutions. So maybe one thing that differs in the way that you're thinking about running an experiment has to do with teaching kids to empathize with one another. And so maybe there are a number of traditional anti-bullying programs that get students to come together and talk about their own feelings, but not trying to get them to empathize with the feelings of others, right? So if you gave the traditional anti-bullying campaign as a control for your twist on the anti-bullying campaign, adding in empathy, then what you have are two groups that are nearly identical, right? If you've randomly assigned them, you should have equal numbers of rich groups in both of the samples. You should have equal numbers of rural schools and urban schools and all of those other factors that could contribute, right? So you have all of those things. And in addition, you should have equivalent expectations across the experimental and control group. Because you haven't told them, oh, okay, you guys were going to teach you about empathy, and you guys were not going to teach you about empathy. Everyone just knows that we're doing an anti-bullying campaign, and they're not talking back and forth with one another because they don't know what the other schools are. Does that make sense? So in a situation like that, it's actually better not to do nothing, because if you do nothing, then what you are comparing are two things that aren't really well balanced out for one another. If you think about medical research, imagine that you're working for some company and you've come up with some new drug that you believe is going to be effective at fighting cancer. How do you test the effectiveness of this drug? Do you give one group of participants the drug and then another group of participants nothing? Well, that's one way to do it, but there are already cancer drugs out there. There are already good cancer drugs out there. So it would be better to do, one group with the cancer drug and with the new one, and another group with the pre-existing cancer medication to see if there are differences in those two things that you're already expecting to be effective. So in that sense, the control doesn't have to be no manipulation or there's nothing happening. Now, there's another point that I mentioned to Cass that I'm aware of, but you guys aren't necessarily aware of yet. So in talking about experimental methods, there are a number of different things that we can look at. We can look at a single independent variable, like anti-bullying campaign. And we can look at a number of different levels of the anti-bullying campaign. We could talk about no bullying campaign, right? The true control, or the pre-existing bullying campaigns, or our new anti-bullying campaigns. Now, in a situation like that, you have one independent variable, but it has three levels. Nothing, the old, or the status quo, and the new. Now, in the simplest types of experiments, you have a single independent variable with only two levels. So today we're going to talk about those types of experiments and how you analyze the data from them. And to analyze the data from an experiment where you have a single independent variable with only two levels, where are my stats people? What type of test do you need to do? A what?
Detail test, or?
I don't care about the tails. thought I heard, yes, a t-test. We need to do a t-test. And a t-test can be used to do a number of different things. It can just look at a single sample, or it can be used to compare two samples. But if we have a situation where we have no anti-bullying, status quo anti-bullying, and new anti-bullying, we don't just have two groups to compare, we have three. And in order to compare three groups, we need more advanced statistical techniques like ANOVA, analysis of variance. And we'll talk about that in the upcoming weeks. For right now, we're going to start simple with the t-test. Did you have a question?
No.
Okay, I thought I saw it. All right, so one other thing that I wanted to hit before we move on and start talking about t-tests was internal validity, and I'm not sure if I actually defined that last class. Did we define internal validity? So we got head shake no. Does anyone have an idea? So it has something to do with validity, which we said is doing what you think that you're doing, or being what you think it should be. We talked about external validity, which is whether or not our sample represents the population that we're interested in, or whether our methods are going to match what's out there in the real world, right? So with internal validity, what do you think that might have to do with? Internal. What did we talk about last class in terms of what distinguishes correlational studies from experimental ones? The manipulation, yes. So with correlational studies, Ttest, we had no manipulation of the IV. And with our experiment, we had a manipulation. And in what other way did these two types of studies vastly differ from one another? Claims about causation. So we had weak claims. And strong claims. So internal validity is about this stuff. So can you figure it out? If you had to guess, which type of study would have more internal validity? So internal validity, not independent variable there, but internal validity.
Experiment.
Experiment. So he's saying higher with an experiment. Let's do a quick poll. So how many people think an experiment has higher internal validity? How many people think correlational study has higher internal validity? One, maybe 1.5. Were you raising your hand for that one? Okay. Well, so most people said this one they thought would have internal validity. Why? We're able to manipulate something. So internal validity is all about making claims of causation. So because we are manipulating the independent variable here, we can make stronger claims about causal effects. Why? What does manipulating the independent variable get us that just measuring it doesn't?
You can make sure that it's not confounded.
Yeah, that's exactly it. If we manipulate the independent variable appropriately, that independent variable, the changes with it or the variations in it, won't be confounded with any extraneous variables, right? We can't do that with a correlational study. And because we can't do that in a correlational study, we can't be sure that our independent variable isn't confounded. With a proper experiment, we can come as close to being sure as possible, which is why we can make stronger claims. So internal validity is all about the strength of causal claims. And the reason that experiments have so much more of it is because we're manipulating that independent variable in a way that allows us to potentially rule out any legitimate claims that there's a confound. Does that make sense? this brings up one other point that the student mentioned to me when they came into my office today. And that was something about not understanding some of the things that I'm doing in class. And I said, if that happens, you should raise your hand and ask a question. So if you guys don't understand something, stop me. Because if no one says anything, I assume that you have it, which is not always the right assumption to make. But unless you guys stop me, I will continue going on. All right. So, some of you have had stats. So let's talk about t-tests. What different types of t-tests are there? There are 3. We've got paired t-tests. Yes. I'm not so interested in the tails, because you can have tails, single or 2 tails, regardless of the type of t-test that you're running.
Is there a difference between within and between?
Yes, there is a huge difference for within and between. And in fact, the paired relates to that. So within and between, what's the difference between within and between? You said, is there a difference between within and between? And yes, there is. What's within? What's between?
When it's, like if it has to do with if the participants are in multiple conditions to compare results to, and then one of them isn't. And I can't remember which one.
Well, I wrote it up here for you because I thought you were explaining them in the order that you
No,
said.
I
And this order is absolutely right. With a within subjects design, you have participants participating in multiple conditions. And what you do is you compare their participation in one condition to their participation in another condition. So each participant or each subject serves as their own control. With the between subjects design, you don't have that. With the between subjects design, what you have are, let me add one more word here. Each participant in multiple conditions, and here I'm going to say different participants in different conditions. Let's adjust the definition because I was using what you gave me at the time. So within subjects, between subjects, within, each person participates in the different conditions. Between, different participants participate in the different conditions. So last class, one of the ways that I talked about studying anti-bullying was to go in and watch kids on the playground before the intervention, right? Do the intervention and then come back and watch those same kids afterwards. What type of a design is that? Is that within or between? It's within, right? Because you're looking at the kids, you do your manipulation, and then you go back and you look at those same kids, or you look at the same school, or you look at the same whatever it is that you're interested in. Now compare that with something else. 2 schools, or multiple groups of schools, and some schools get the new anti-bullying stuff, whereas the other schools get the traditional anti-bullying stuff. What type of design is that? Between. That's exactly right. So this is like post test, and this would be like different schools. Which type of design would be better if you could do it? within. Why?
Because you can see how the same people change.
Yeah, you've got more control. Each person is balanced with themselves. So if you can have a choice in how you design something, a within subjects design is much better. Now, if we wanted to compare traditional anti-bullying with newfangled anti-bullying, it might be difficult to do the comparison, right? Because if you present one and measure after that, and then you do the next one, well, you've actually had both at the time that you measure at the end, right? So there are some situations where it's really not logical to do a within subjects design. So, paired T-test. That's one of our types of T-test. And what type of design goes with paired? Within or between? Does anyone know the other type of T-test that's related to the paired? Because then we might be able to figure it out more easily.
But the independent?
Independent. Beautiful. So we have a paired T-test versus independent T-test. What sounds more like it would go with a within design? Paired. Why?
Because each subject or participant is paired with their own results.
It's so logical. Each participant or each subject is paired with themselves. You don't have to do this. There are some situations where maybe you want to look at, I don't know, the effectiveness of some learning strategy on test performance. And I'm going to have some people make up mnemonics as they study, and other people I'm just going to have them study. Okay? Now, what things besides the studying technique could have a big impact on someone's exam performance?
Wait, sorry, can you repeat that?
Which part? I'll go with the last part. So, what besides how someone studies could affect how they perform on an exam? Sleep?
If they ate.
What's the biggest one? If you get 100 on some test, what do your friends say?
Intelligence.
Intelligence. I would say intelligence is probably a better predictor than sleep, but maybe not. But we could pair people based on intelligence, right? Imagine, and here we're not going to do completely random sampling. We're going to be, or not, I'm sorry. I meant random assignment. We're not going to do completely random assignment. We're going to do paired random assignment. So I take my random sample. I have a whole bunch of people. And then I want to assign them to either use mnemonics or use just study. Okay? Now, I think that intelligence is going to affect the outcomes. And I want to control for intelligence, right? Now, random assignment's going to control for that just by itself, right? Because half of the smartest people should end up in the one group and half of the smartest people should end up in the other. However, if I'm randomly assigning people, I can't guarantee that it will end up that way, right? So what can I do to guarantee that half of the smartest are going to end up?
IQ test and then separate them.
That's exactly right. So I give them some type of IQ test, maybe something quick that I can measure, rapidly. And then what I'll do is I'll take the two people that scored the best, flip a coin. You're going in one, you're going in another. Then I take the next two people, flip a coin. You're going in one, you're going in the other. Does that make sense? So for each pair, one's going in one direction and one's going in the opposite. Okay, so we've paired people up, we've split them up. Now we don't have each person serving as their own control, but what we do have is each person being paired with someone who's roughly equivalent on the extraneous variable that we want to control. Does that make sense? So that would be a between subjects design that we could still use a paired t-test for. So just knowing the type of design isn't automatically going to determine how, what t-test we're going to use. And between. How about independent? Can we use within and between for independent? Shaking your head. Why not?
Because of the within, it's gotta be paired with something.
Yeah, if it's within, you've already got this pairing. So if we don't have any of this type of pairing, we can't include within, so this is between them. Does that make sense? You want to know the last type of t-test? Single sample? That's you who said it?
Yeah, I thought that's what it was.
That is what it is.
Okay.
I'm going to say one sample. One sample, single sample, they're the same thing. Mine is just, it has fewer syllables. So, one sample. What on earth is a one sample t-test? Here we, compare anti-bullying versus nothing, or traditional versus new. We could do the same thing here. What about here?
Yeah. Like you can do old school and new school, or you can add more old school, look at it.
Okay, so we have to pick one. Let's say we're going to pick our new school. Because the old school is old school, and we want to push the boundaries of science forward. Okay, so let's talk about what t-tests do. What do they allow us to do? What types of claims do we make after performing a t-test, or could we make?
Reject or fail to reject.
Okay, so there are some null hypotheses, right? And then we either reject the null hypothesis or fail to reject it based on the p-value, right? So that's beautiful. So what do the null hypotheses look for these different types of tests? Null. So we have anti-bullying versus, or the new anti-bullying versus old anti-bullying. What's a null hypothesis?
So there's no difference.
There's no difference. There's no difference. It doesn't matter whether you get the new anti-bullying or the old anti-bullying. You're going to see exactly the same amount of violence on the playground, right? And usually when we're talking about no difference, we're talking about a difference in means, right? So the schools, we're going to look at the mean number of violent behaviors for all of the schools that have had the new anti-bullying. And we're going to look at the mean number of violent behaviors for the schools that had the old anti-bullying. Does that make sense? How about here? So what? Same thing. Yep. No diff between, I'm going to put mu, between mu's, between the means. How about for one sample?
It gets better or it gets worse? I'm thinking of it in terms of our little, when we write it with the arrows.
Yeah.
With the alligators. Like, because that was
Oh.
equal to or not equal to.
So,
That makes sense.
saying like mu1 equals mu2. Like that.
Yeah.
Yeah.
They don't equal. Anyone doesn't equal.
No, the null
Oh, there's
hypothesis.
no difference. Oh, yeah.
Null hypothesis, right? So your alternative would be that it's greater or less than the alligators. So here you said it's greater or less than, but then what? What's the null? Let's talk about your water again, your smart water, because this will make more sense, I think. So remember when we were talking about the water and we were talking about Coca-Cola and we wanted to see if Coke's claims were true? What were we talking about? What was our null hypothesis then?
But it didn't have the same amount of everything.
Not that it didn't have the same amount every time, because we expect it to be different almost every time, right? Some are going to have more, some are going to have less. Had to do with the amount.
And there by 1 standard deviation.
Ah, so you're thinking about
Yeah.
when we had enough evidence to reject the null hypothesis. But what was the null hypothesis? So here we have mean equals mean, mean equals mean. We're going to have something here, mean equals, sorry for the, how much water does that smart water have?
700.
700 milliliters. What was the null hypothesis? What's the status quo? If you wanted to sue them,
That was below or above a certain
below or above a certain
amount.
certain amount. Right? And we said for that water it should be 700 milliliters. That's exactly right. That's the null hypothesis for our one sample t-test. That the mean is equal to a certain amount, right? If it's above or below that mean, then we have cause potentially to sue them. So, let's talk about what a t-test looks like. T equals, for a one sample t-test, does anyone know the equation? There's a mean in it. So I'll give you the mean. So mean, that's mu. Okay. You guys see my cousin Vinny? So it's actually a great movie about law. And the guy's from New Jersey, I believe, and he's like, these two Utes. And the judge is like, Utes? Utes? Oh, I'm sorry, Utes. Anyways, yes, mu. Mu. What are we comparing the mean against? Yeah, I got it over there. Certain amount. So what we're going to do is take a deviation score, basically. The mean minus certain amount. And under the null hypothesis, what are we predicting this to be? We're predicting those two things to be the same. So the hypothesis is that that numerator should be 0. Right? Because if the mean that we observe really is that certain amount, then that's going to really support the null hypothesis. So we have the mean minus some certain amount, and this is basically just a deviation. We can also think about it in terms of variability. How much variation was there between what we observed and what we expected? Right? This is what we were expecting. This is what we observed. How big is that difference? So in some way, this is very similar to what formula that we've seen before. Standard deviation, that's exactly right, right? We were comparing what we observed, each value of x, versus what we would expect, which was the unbiased estimate of the mean. So here, again, we have something that's very similar to that. So beautiful. Okay, so we have some deviation. What can we compare that deviation or that variation to figure out whether or not that variation is meaningful or is just indicative of random chance? Say what?
I know I'm going to be wrong.
Go for it.
R.
Yeah,
Yeah.
wrong. But what is R made of? So R is the correlation coefficient. And what things make up the correlation coefficient? Because they're related. All these stats are. It's made up of covariance, right? Which is closely related to what?
X, Y, and X, S, X.
Right. Those are the covariances over the standard deviations multiplied by one another. So that's going to tell us how strong the relationship is, or how much those things go together compared to how they could go together. We have some variation. We want to know if this variation is likely or unlikely to be due to chance. How do we figure this out when we flip the coin? We did some math, right? And then like a class later, we talked about something. We talked about the sampling distribution of the means. And what described the means that we would expect to see? There was a statistic. The standard error of means. That's exactly right. So we have the variation in the mean that we observed with the mean that we expected, right? So that's like an error in what our expectation was compared to what it actually was. And we compare this to the standard error of the mean. And by doing this, we'll get a value for t that then we can either look up in a table or we can use R and just figure it out directly like that and see how interesting that is. So what's the formula for the standard error of the mean? Square root
I have standard deviation of a square root of a number.
So you didn't have this, you had standard deviation over the square root of the number, which if we express like this, would be that. Same thing. So for a single sample or a one sample t-test, all we need to do is look at our mean, compare that to what we expected, and then compare all of this to the standard error of the mean. If this value of t is large, I'm going to say, actually, I'm going to use larger. Larger, more or less significant. Larger is less significant. How many of you guys agree with that? Larger is less significant. 1, 2. So the larger t is, the less significant t is. How many people would say the larger t is more significant? So how many would agree with that? 1. Dakota, you want to weigh in?
Probably larger.
Larger?
More significant.
So we've got 2 versus 2. Oh, yeah. Okay, so imagine we've got 700 milliliters. This is what we expect the mean to be. And we observe 710. And knowing what the standard error of the mean is, we can create some distribution that looks like that, right? Or, since we thought that it would be here at 700, we could draw the same distribution like that. Imagine that situation where you have some difference between what you observed and what you were expecting versus, I'm just going to try to draw these the same. what would be more significant? Top or bottom? So, more, how many people think the top is more significant? 1, 2, 3, 4, 5. How many think this is more significant? Sweet. Well, at least the majority's got this one right.
Dang it.
Right? So think about it. We have our expectation underneath the null hypothesis, and we estimate how much variance there is by using our unbiased estimate of the population variance, right? And then we know about the sampling error of the mean, so we transform that variance estimate by dividing it by n and taking the square root of that whole thing to create what this distribution looks like. And then what we need to do, if you're doing stats, you've probably drawn these things all the time, is we look for values that fall beyond a certain point. And look how far this is beyond that point. Compare that with, sorry, I didn't draw them. But this, that's within it.
Okay.
Does that make sense? So here, the sends, I'm trying to draw the sends exactly the same in both situations, right? What I wanted to show you is that when mean minus a certain value, as this difference gets bigger, t is also going to get bigger, right? Because if the send is the same for both of those situations, the bigger this is, the bigger t is. The bigger t is, now let's have a vote. Bigger t is less significant or more significant?
More.
How many for less? How many for more? Yes, good. Bigger the t, the more significant it is. Woohoo! So, this is what we're doing with our one sample t-test level. Now, before we move on, I want to point out something. So in the one sample situation, we said that the mean was equal to a certain amount. Here we were saying that the mean was equal to, the mean is equal to, not to itself, to the other mean. And what's the other mean? It's just a certain value. Right? We observe a mean, it's that value. So if you think about it in that sense, this second mean is roughly equivalent to a certain amount. Except in the one sample test, we already know what the amount should be from the beginning, right? It should be 700. It should be 50 milligrams of caffeine. It should be X many calories. It should be N number of violent episodes at a school. So when we said pick one up here, we could do this with the one sample t-test. Imagine a situation that we knew the average number of violent outbreaks within a certain time frame after a particular anti-bullying intervention. It's been well studied. Look at this, you do this type of anti-bullying thing, and you'll see on average this many types of violent behaviors. And there's some variability, right? We expect that. But if we know what the average was, if we had an idea for a new anti-bullying intervention and we didn't have enough money to compare that directly to some control group, what could we do? We could say, well, we know after this anti-bullying campaign, you get this many numbers of behaviors. So let's see if our new anti-bullying campaign produces the same number of behaviors, right? So in this situation, we would have to know what that number of behaviors is. In this situation, maybe we don't know what that number of behaviors is, but we can measure it, right? Get two groups. Some schools get the new stuff, some schools get the old stuff. We're going to count the number of violent episodes at both schools, or both sets of schools, and come up with the means for each of those sets of schools. And again, we could have something could look like this or could look like this. Imagine that these aren't milliliters in the water. Instead, they're numbers of violent outbreaks. These are schools, so imagine like pushing down.
That's a lot of violent outbreaks. Cool.
It depends what type of school you're in. I was peed on and stabbed with scissors and stuff. That was rough. Yeah. My wife, she's like, how is that possible? And she went to a much larger school, so I'm shocked. But I was in a more urban area. But anyway, you can imagine, right? So there are some number of violent episodes with the new thing and some number of violent episodes with the traditional or the old school. And what you want to do is you want to see whether these two differences are the same. So again, we are going to have a formula for T, and it's going to look a lot like this. So this is one sample. This is going to be independent sample. And here, T, actually, since we don't have the true mean, we are estimating these. That should be 1, and this should be our unbiased estimate. So, again, we're going to have one of the means that we observe. And what are we going to compare to? You want? The other mean. That's exactly right. Beautiful. Or maybe we want to say y. Keep things straight. And what are we going to divide that by? We divided this by the standard error of the mean. What are we going to divide that by? The standard error of the mean. So what?
I was saying I had it right.
You should have spoke up.
I
believed in you.
Oh, I did that.
Now, the form of this standard error of the mean is slightly different than the form for this standard error of the mean. Why do you think that might be? This chocolate's horrible. Too tiny. How many means are we estimating in this situation? 1. We have one mean that we're estimating, right? Our new intervention. How many variances are we estimating in this situation? None or one? Good question. Which is it? Because one of those is right. 1, that's exactly right. We're making one estimate of the population variance. Right? How many means are we estimating over here? 2. How many estimates of the population variance do we have over here? 2. Right now, the null hypothesis says that there's no difference. And we can consider this as not just no difference between the means, but also no difference between the variances, right? They should be exactly the same thing. So if that's the case, then each one of the variances, so the variance estimate for X and the variance estimate for Y, which could be the new program and the old program, those are both thought to be estimating the same thing. So our standard error of the mean is going to look a little bit different. It's going to look very similar, but a little different. I'm just going to go back to X, because that's better. How are these two formulas similar? How are they different? Yeah, we're combining the two. Right? We've got two estimates. We need to combine both of them. So the numerator is almost identical, right? It is one mean minus a certain amount, one mean minus a certain amount. No big deal. The bottom is nearly identical. They're both standard error of the means. But because we have one estimate of the variance that we use to figure out what the standard error of the mean is, in that situation, we only have one thing to include in our estimate for the standard error of the mean. Here, however, we've got two estimates, so let's put them together to come up with our estimate. But notice, the form, it's exactly the same, we just have an additional piece. So it's not that scary, it's not that hard. What time do we got? We've got 2 minutes. All right. I was going to say on Monday, but not on Monday. Well, maybe on Monday. So on Monday, we'll do the review. If you guys don't have questions, we're going to jump into paired T-tests to take a look and see what happens with the paired T-tests and why paired T-tests are so wonderful. See you guys later.